Very good evening, everyone. On behalf of the entire Radiomitra team, it is with great enthusiasm that I extend a warm and heartfelt welcome to Sharat Prabhu sir, who will be guiding us through the exciting journey of this 5-day International Space Olympiad training. Sharat sir is not just a seasoned physicist, but an inspiring science communicator with a deep passion for promoting scientific thinking and education. With an impressive academic background, including a postgraduate degree in physics and an MPhil specialization in astrophysics, Sharat sir's expertise in high energy astrophysics, particularly his research in gamma ray burst, speaks volumes about his dedication and curiosity in unraveling the mysteries of the universe. Beyond his academic achievements, Sharat sir is a multifaceted individual whose contributions to science popularization are truly remarkable. Hosting the Astronomy TV show Arike Agasham on the Malayalam education channel Victors, he has captured the imagination of a vast audience, making complex scientific concepts accessible and engaging. We are honored and thrilled to have you with us, Sharat sir, to lead this training program. Let us all take this opportunity to immerse ourselves in the world of space science and astrophysics under the guidance of such an accomplished mentor. Warm welcome, Sharat sir. Over to you.
Thank you, Team Edumitra, for this wonderful opportunity to interact with this wonderful kids. Once again, warm welcome to all of you. And I'll be here for a couple of days discussing some of the topics in your syllabus. And I will be giving you an overview about the distance, the measurements in astronomy, then also about the stars and all. Okay, and regarding the cosmology part, my fellow teacher will deal that. So today we will start by the formal session that will last for 1 hour. So if you have any doubt during the formal session, you can put it in the chat, and at the end of the session we can have a direct interactive session. For that I will unmute you all and we can have that discussion directly, or even you can put in the chat. So I will try to answer as much as possible within the time limit, because we have only half an hour remaining after the formal session. So during that I will try to answer as much as possible, and during the class if you have any doubt you can put it in the chat. Okay, so that is what you can do. So during the class, no direct talk will be entertained because you will be mute for that time. Okay, so once again thank you so much. So let me begin. So let's share the screen. So I hope this is visible. And one more thing, I think there are some familiar faces there already been in my class, I think. So happy to see once again. I don't remember everyone, but I remember some of the names and your photos there. Okay. And the topic is not the measurements in astronomy. I have given the title like that, but because the measurement in astronomy is a vast thing, which needs a lot of understanding of physics and mathematics. But whatever we can learn with the knowledge of your level, that is your senior and super seniors level, within that limit, how much you can grasp, that is actually included in this session as well as in your syllabus. Actually measuring temperature, measuring some maybe the constituents, the relative abundance of materials inside a star or something like that. Those things are actually beyond your level, but we will try to we will only include the whatever things that you can learn easily. Okay, so as you might know, the astronomy, the measurements are done not like this as you see here. To measure the circumference of Earth, we cannot use a tape like this, a measuring tape like this, or to measure the temperature of sun, we cannot use a thermometer like this, or for measuring the constituents of a sun, we cannot use the usual chemical methods or what you employ in your chemistry lab, that we cannot use. So we are actually using some other things, we can call it as some kind of remote methods, because we are not actually touching the subject, or we are not actually collecting the material. Without even touching, remotely we are measuring all almost all kind of things. Okay, so maybe when you need something for calculation or some project, you will go to Google and search for what is the mass of Earth, what is the mass of Sun, or what is the size of Sun, or something like that. What is the pressure inside, or what is happening inside? So all these things are actually, you get an answer in the internet, like a number will be there for your answer. As your answer, there will be a number. But all these numbers are not measured directly, but they are all measured by analyzing only one thing that you receive from the celestial object that is star. Or there are some other things that you receive from celestial object, but apart from that, almost the 90% or more than 95% of the thing that astronomers use to study the space or the cosmos is by analyzing the light. Okay, so in light, in the sense, so when you hear the word light, there is a problem in that. So when you hear that word light, so the light usually means the light that what we see with our eye. So that is the common notion of eye. No, that is the common notion of light. But in astronomy, when you hear the word light, it doesn't just the light that we can see, that the human eye can detect. So there are other kind of light which we can see. I'm not audible? Hello? Hello? Uh, so I got a message, I'm not audible. What about others? Can you just put in the chat whether I am audible or not? Yeah, okay, thank you. I think, Kaivalya, it's a problem at your side. Please do check. Okay, others can hear me well. Okay. Yeah, okay. So that's about it. So yeah, it's all fine. So we are, or the astronomers are always keeping their telescope open for light. So again, light, not in just the sense of the visible light or the light which is sensible just for our human eye. There are other kind of lights. Okay, I'm using the word lights in the sense that there are many types of lights are there. In science or in the universe itself or everywhere, there are many kinds of light, and all those kinds of lights are being used in astronomy. So some examples are something like the X-ray, that that you won't see a flash when an X-ray is taking, because you cannot see that, but the X-ray film or the digital X-ray receiver is able to capture that light and make a picture of your bones like this. And inside a microwave oven, you cannot see any flame or anything, but actually there is microwave is coming from the klystrons from there. That is the that generators are there, and this is an image of an infrared, from an infrared camera. Okay, but even though you cannot see like this, infrared cameras are actually seeing the infrared and converting it into a visible image which we can see like this. And that Wi-Fi, radio, all these kind of things are working in radio frequency waves. Okay, so light is considered to be something called electromagnetic waves. Okay, in generally we call them EM waves or electromagnetic waves. So what do you mean by electromagnetic waves? So in the case of a wave, that wave is not a static thing. Any wave, okay, you can imagine a wave, even a sea wave you can imagine. Okay, so a wave in the sea you can imagine. It is not a stationary thing, it is a moving thing. So its peak will be there. I can draw like this, but actually this is a static picture of a wave. So if in reality this top portion, that is the crust, and the trough, this should actually moving in this direction. So something is varying, at the same time it is moving as well. Okay, so that is changing in position and changing in time, so that we can call it as a wave. Okay, similarly in the case of a sound wave, when I am talking like this, you are hearing my voice through it is coming through the whatever electronic systems are there. Anyway, finally you are hearing my voice, some kind of a wave called uh, sound waves, which is the change of something called a pressure. Okay, the pressure variation is what you are hearing. The air pressure variation is what you are hearing as my sound. Okay, then in the case of a sea wave, what you are seeing in the sea, it is actually the height of the wave is actually changing. You can see height of the wave, how height of the water is actually changing. So for every wave, there should be something varying. And you can imagine something else. Actually, if you take a rope and knot it at one side, and you can actually oscillate something like this, you can wave it using your hand. And in that case, the height of that certain portion is changing. So that height is changing. So in every kind of wave, there is something that is changes. So in the case of a light, okay, in any type of light, what is changing is actually two things. One is electric field, and the other is magnetic field. Okay, and they are coupled together as well. So electric field and magnetic field, they are coupled together and varying with respect to time and space, and they are called electromagnetic waves. But in astronomy, instead of saying electromagnetic waves, we call them as light. So in astronomy, light means all kind of lights that starts from gamma rays and ends at radio waves. So these are the, and you know that for a what is called for a wave, there are some parameters, and one of the interesting parameters is called wavelength. Wavelength is the gap between the two crust or two troughs. Okay, so you can see that radio waves has this much wavelength of the order of 1 meter to some 10 raised to 3000 meters of the order. Okay, so 1 meter is the wavelength for a radio wave. At the same time, when you come here, you can see that for a gamma ray, it is actually 10 raised to minus 5 nanometer. So nanometer, I hope you know that it is 10 to the power minus 9 meter, or billionth of a meter. Okay, something like that. So when you come to gamma rays, okay, if you arrange it in this order, when you arrange the different types of light in this order, it has another name. It is called the electromagnetic spectrum. Electromagnetic spectrum. So spectrum is an arrangement of different types of things. So this is called a spectrum of things, and this is gamma rays, then X-rays. So when you, in this particular image, okay, if you go start from the left to right, you can see that the wavelength is increasing. Okay, the gap is increasing. It is so visible. It's obvious from this picture. And also you can see that energy actually decreases from left to right, or in other words, it increases from right to left. Okay, the frequency is also opposite. So just you can see that, just not just understand that variations. Okay, instead of by hearting those values, you can just understand that the gamma rays are so energetic than the visible light. Okay, so that comparative knowledge should be there instead of by hearting what is the exact frequency or something like. So there are different kind of lights, and all these kind of lights are actually coming from celestial objects. So even take the case of sun is emitting light in all these kind of types of lights. The sun is emitting visible, obviously, ultraviolet, infrared, X-rays, gamma rays, but the amount it emits will change. Okay, so the sun mostly emits in visible light, so other kind of lights are actually less in amount. So it is actually emitting different kinds of light. It's fine, and but all the lights cannot reach the Earth's surface. So imagine that this line is the Earth's surface or something like that. So it is not the Earth's surface. So imagine that this is the Earth, and here in the axis it is showing the opacity of atmosphere. That means how much opaque the atmosphere is for different kind of lights. So here, if you take the case of gamma rays or X-rays and ultraviolet, the opacity is 100%. You can see that line here. So 100% opaque means it is opaque. So gamma rays and X-rays from celestial objects cannot reach on the Earth's atmosphere. At the same time, if you look at the visible part, the visible light can almost reach there. There is some hindrance for that, something, some 10% opacity is there, but it's fine, still we get it. But in the case of radio waves, if you see, you can see that it is 100% transparent or 0% opaque. Okay, it is transparent. Atmosphere is transparent for radio waves. So we can place radio telescopes and visible telescopes, and also you can see that some part of infrared is coming, so that some infrared measurements, and some nearby maybe some ultraviolet. So the beginning of ultraviolet maybe can be measured from the surface of Earth. Okay, but all the other things, something like gamma ray or X-ray or maybe in many of the part of the infrared if you want to measure them, you have to go to space. So that is the one main thing that we use the space telescope, because we cannot get all the wavelength here on the Earth's surface. That is why we have different kind of telescopes are there. So I hope you know that this is the Chandra X-ray, James Webb Space Telescope, Hubble Space Telescope. This is another telescope, radio telescope. This is an optical telescope. So optical telescope means that is observing in the visible light. But apart from visible, it will also observe in some part of the infrared as well. So that is this kind of different. That is why we do have different kind of telescope as well. Sometimes the X-ray telescope even doesn't looks like a telescope. There is no opening or any mirror or lens you cannot found here, but there are kind of lens which is capable of focusing X-rays there, and this looks like simply a dish antenna. It's actually a dish antenna, but it's a telescope as well. Okay. So now I said that most of the light or most of the observations, analysis and science is happening in astronomy is from the light. Okay. Other than that, there are some other things are there, and even direct objects, direct sampling is also there. Something like we brought materials from moon here and we analyze that. Okay, but it's, you know, that when compared with the vastness of the universe or the vastness of the measurement that we made in astronomy, it is not even a fraction. Okay, it's so less. But apart from this, most there is some other things, and they are called gravitational waves are there, that is being monitored, or there are gravitational observatories are there. Apart from light, cosmic rays are there, then neutrinos are there. So neutrinos we will discuss later when we learn about the stars, don't worry. And gravitational waves you may know. Okay, so I'm not going to explain that right now, it's not the part of right now. Okay, anyway, if needed we will discuss at the end. So anyway, mostly what we observe or we analyze is light. Okay, so in using those light, we have to measure all the things. So like the temperature, like the distance, like the mass, like the pressure. So whatever quantity that you heard in astronomy, almost all of them has to be measured only by observing the light. So that is again a curious thing, how we can measure them. So how we can measure the temperature without using a thermometer, or how we can measure the weight of a planet without using a weighing balance. Okay, so there are methods for that, and those methods are actually so much interesting, and it's an interesting topic in astronomy. But we are not going to all of them. We are not discussing about how we measure the temperature. We are not going to discuss about how we measure the pressure, maybe how we measure the relative relative abundance of materials. But we will discuss some of them which is actually accessible for you right now at your level of knowledge. Okay, so that we will discuss here. And one of the most easily understandable, at the same time interesting thing is the distance. So how far away the things are actually maybe the first question that comes to our mind when you think about the celestial object other than what it is made of. Okay, so for that we have to measure the distance to those objects. So distance to objects are actually being measured using using several number of methods, not just a single method. Okay, so in astronomy we cannot employ a single method to measure all types of distances. Okay, that means astronomy as well, you know that the distance is so vast. Okay, that means maybe within the solar system, maybe some millions or billions of kilometers, that's okay. But if you go to nearby stars, it becomes of the order of light year. So light year, I hope you know that light year is a unit that is used to measure the distance in astronomy, usually written as Ly, and it is read as light year. Okay, and light year is a unit of measuring distance, and 1 light year is the distance traveled by light in a year. Okay, distance traveled by light in a year. In a second, the light travel 300,000 kilometer, and in a minute it can travel, just multiply it with a 60, again with a 60 in an hour, then again with a 24 in a day, and 365. And the product of this, okay, this thing, okay, if you multiply all these numbers together and you get an answer in kilometer, that huge number is called a 1 light year. Okay, so now the problem with or why do have these different methods? Okay, so I will explain almost all of them to you, don't worry about that. But before going to that, you can see that it is written something like this. You see, first one, solar system, and this is a boundary here. Okay, so this is the range up to which you can use the method of radar ranging. So I am not explaining radar ranging right now, but you understand what is the meaning of this picture actually. So radar ranging can only be used within the solar system. And you can see then another thing that is called a parallax. Okay, so the parallax can be used for nearby stars. That, what is the meaning of that? We cannot use the radar ranging for nearby star. So to measure the distance to nearby stars, we have to employ another method that is called a parallax. Okay, then for Milky Way, the other apart from the nearby stars, if you want to measure the distance to farther away stars, and if you want to map the structure of our galaxy and all, we have to map out all the stars, distance to all the stars and all, then we cannot use the parallax method even. So we have to shift to I'm not saying that it is not completely unusable, but it is better to use main sequence fitting. It is another method. Okay, so we have to use that there. And for nearby galaxies and all, it is better to use what is called Cepheid variables. So beyond this Cepheid variables or nearby galaxies, we cannot use the parallax method at all. So it has a limitation. So every method that we employ for finding the distances, the problem is that everything has a limitation. Okay, so if you want to measure the distance to other galaxy clusters, then we have to employ something like the supernova method. Okay, or white dwarf supernova or Telly-Fisher relation, something like that. Okay, then even beyond that, if you want to measure the distance, you have to use the Hubble's law. So it is something like a ladder. Okay, so each step of distance has to employ a different method. So you can imagine it like a different steps, and this is called the cosmic distance ladder. Okay. So this different steps of measuring distance for different range of distance is called the cosmic distance ladder. So now we will go to one, not all of them, at least one or two of them, one by one. So we will discuss radar ranging. It is so simple. Then parallax method we will discuss. Then main sequence fitting won't be, because I will give you a glimpse of that when we learn about the stars and all, but won't be learning that. Then Cepheid variables, then white dwarf supernova we will learn. And in the last session you will learn about method. Okay, that we won't be discussing today. Okay, so these are the different method of distance measuring, and let's go one by one. So the radar ranging is the most easy one because it uses radar. Radar means, you know, that it is the radio detection and ranging. So you can see here in this figure itself, you know that we are sending a radio wave, okay, to maybe to the nearby planet, and that radio wave will be reflected back to our detector. So reach Venus and come back. So when it goes and come back, you can see that you can find how long it took to reach there and come back. Okay, so we get the time. Okay, so what we are doing, we are sending a pulse to the planet. Okay, so suppose Venus is here. Okay, so Venus is here, we are sending a pulse and it will come back. Let t be the time taken for that. Okay, so certain time is taken. Now since radio wave is a kind of a wave that is light, okay, so the speed of light is simply c, or c means 3 lakh kilometer per second. So you know the speed of that light, then you know the time. So from the speed and time, if you multiply c with the t, then you get the distance. C distance is equal to c into t, or simply distance is equal to speed into time. So this is one of the simple equation that you might be learned in your school classes maybe. So speed into time is the distance. So same thing can be employed here. You know the speed of light already, and what is the time taken for going and coming back. The problem is that it is the time for reaching there and coming back. So it is actually 2 times the d. Okay, so it is traveled to the moon, to the Venus and came back. So it is 2 times the d. So actual distance is d is equal to ct by 2, half of that. Simple, because we are actually taking the time taken for the round trip. but there is no need of that round trip. For the distance, we need the only one way. So CT by 2, that is simple. Okay, so this is the method that is called the radar ranging. So this method is also used for finding the distance to aircraft and all, and it can also use to measure the speed of aircrafts kind of things. So radar are actually much more application are there for ground-based observations as well. Okay, so now let's go. But the problem of radar ranging is that it cannot be used for far away things. Suppose if you want to measure the distance to a nearby star, you can send radio pulses, but the problem is that you have to send strong pulses to reach the star. And one more thing, if you want to, suppose you want to measure the distance to the Proxima Centauri, which is at some 4 light years away. So we have to send that pulse right now, and it will come back only after 8 years, because 4 years will take to reach there and 4 years will take to come back. And that is not just the problem. We can wait for 8 years, no problem at all. But the other problem is that when it reaches there, it will only reflect a tiny part of that. So you have to send such strong signal to reach there. So that is also again a problem. So that is why we cannot use that radar ranging method beyond this. Okay, so that is why we have the second method, or the next step in your ladder, that is called the parallax method. Okay. So the parallax method is so simple. You can do this simple experiment with your hand. Okay. Okay, so yeah, you can do this simple experiment with your hand. Just hold the thumb in front of you. Okay, just front of the nose, something like some 1 or maybe 5 centimeter away from your nose, exactly in front of your nose, and close one eye and look through the other. So close the right eye and look through the left, and close the left eye and look through the right. So you are alternately looking through either left or right. So by changing that, you can see an interesting thing. Without even moving your thumb, you can get an illusion, or you can get a feel that your finger is jumping in between 2 positions. So first it is at a certain position, then to the other, first, second. So it will keep on changing from one position to another. I hope you can see it right now with your hand. Okay, right now you can do that experiment. There is no need of any additional tool for that. So now just concentrate on that and just have an idea how much your finger shifted, okay, or your thumb, what is the amount of that jump. There is no need to measure that, but just keep that in mind, how much it is shifted. Now at the same moment, now what you have to do, now you have noticed how much it can shift. Now move that hand at that finger an arm length away. Okay, that means you can keep it as farther as you can. Okay, then do the same thing. Okay, that means right now, for the first case, it was near. So suppose this is your eye. Okay, so initially the finger was here, so near to you. Now you have to keep it somewhere here. So in 2 cases, do the same thing and see how that shift changes. So whichever is the long shift, okay, or which gives you the more jump. So if you do that experiment, you can see that when your finger is far away, the shift is small, and when it is closer to you, the shift is more. Okay, so this is an interesting observation that you can see. So actually what happened here, you haven't changed anything. Okay, you haven't changed in the sense that you changed it in the sense that you changed only the point of view. Okay, so the jumping that is not happened because of the actual shift of that object. You haven't moved your finger either to the left or right, but that movement of that left right movement happened because of the perspective of your eye. So whether you are observing through the left or the right, based on that, that shift has been happened. Okay, so what you can infer from here, so when your finger was near to your eye, the shift is maximum, and when it is farther away, shift was, so distance is connected with the and inversely connected to the shift. Okay, so that means in what I hope you know the meaning of this. So if the shift is more, the distance is less. If the shift is less, the distance is more. So shift and distance are connected. That is the idea we got. Now the same thing can be employed to measure the distance to celestial objects. So for that, if you want to measure the distance to moon, assume that, okay, what you have to do is that, suppose the moon is here, suppose this is the moon, and you can imagine this is the earth, and this image is not to scale, and you can observe the moon from two different positions. So I can put two telescopes here. So I am seeing the moon from here and seeing the moon from here. Okay, and in both cases, the background, so assume that there are these three, okay, these three, this is a constellation, assume that, okay, and when you are looking through here from the position A, the moon appears to be in front of these stars, and when you are observing from this position, you will see the moon here. Anyway, this is an exaggerated figure, as you know. Okay, anyway, that is okay. So that's about it. So in two position, so you are seeing the moon at two different position because of you are observing from two different positions. Okay, now you can imagine a triangle like this. Okay, so I'm drawing a triangle, and again I am drawing another one from the center, so that this becomes a right angle triangle, or this both are right angle triangles. Now you know that this is the radius of earth. Okay, this is the radius of earth. Okay, and this is the right angle triangle, and if you know one side, but that is not enough, and if you know one of the angle, either this angle or if you know this angle, I am calling this angle as P, and if you know this angle P and this distance, obviously this is the radius of earth, and if you know the radius of earth and this angle by using the equations of trigonometry, and trigonometry is actually the mathematics of triangles. Okay, so there are some times like sine theta, cos theta, tan theta, etc. So that those things I am not going to discuss here, because you will learn it in the school classes, and it is not that easy to discuss it here, because most of you haven't learned that, and you will learn in the higher classes. That's all. Maybe the super seniors might have some knowledge about that. That's all. So anyway, so this angle is called a parallax angle. Okay, this angle is called a parallax, or parallax angle, or simply parallax. So if you know the parallax and one side, okay, this is something around approximately 6,000 kilometers. So from this you can actually find this distance. Maybe this distance or this distance, they won't make much difference. Okay, anyway, you can easily calculate the distance to the moon. Okay, then the problem is how we get this P. Okay, we want to get the P actually. So for that, you can see that for that parallax angle, you have seen that the moon was initially here, then moon shifted to here. So from this picture, okay, so you got two apparent positions of moon here. So based on how the moon shifted, that shift can be converted into this angle. Okay, so that needs another kind of trigonometry, that is a mathematics of triangles, and that kind of trigonometry is called spherical trigonometry. That is a trigonometry on the surface of a sphere. So using those equations, actually you can calculate, you can convert this change or this shift to this angle, and from that angle you can calculate the parallax. But now there is another problem. You just imagine, for moon this is fine. So now imagine that there is some Saturn is here. Saturn is not this near, just too far away. Then I have to draw the triangle like this. Okay, again I am so good at drawing. So you can see that this is the triangle, and here this is a triangle. Now as the object goes farther and farther, this angle becomes smaller and smaller. Okay, that's obvious actually. So assume that this is the earth, and if this is the planet, then what is the problem? You can see that this angle is so tiny. Okay, if things get, if imagine that a star 4 light years away, the problem is that the angle is so tiny, so that if you place two telescope at two diametrically opposite sides of earth, you cannot even measure this angle. Okay, you won't get that jump. So that is the problem. So in that case, what you can do is that if you increase this distance, now the position B and A, if the B was here and the A was here, I could have been made a much larger triangle so that I can get a bigger angle so that I can measure. But the problem is that on the Earth's surface, what is the maximum I can place two telescopes? That is on two diametrically opposite, one side of Earth and the opposite side. But there is another clever idea. If you observe the same star at two different times, both from the Earth, but now we are observing it in January and again in July. So 6 months apart means the base was actually, in the earlier case, the base was just the 2 times the radius of, you can see that the base was the 2 times the radius of Earth. That means the diameter of Earth. So now I have made that triangles, the base of that triangle so big, something like this. See, it is the diameter of the Earth's orbit. But the thing is that you have to observe that star 6 months apart. That's all. So if you observe it from here and here. So in January, I take an observation of a nearby star. Okay. And with respect to the far away stars, I get a picture like this. And in July, again, I will take another picture. Then I can get the star here. Now compare these two pictures. Okay. Compare these two pictures and you can get that shift. You see this shift you can get. And from that shift, so every star or every object in the sky has a certain kind of coordinates. So coordinate, you know that when you point, this is x-axis, this is y-axis, and we call this point as, maybe if I 3 2, okay, you can call it as, so this is 3 and this is 2. So this is called the coordinates. Similarly, every star has a kind of a coordinate called the right ascension and declination. So I can get the right ascension and declination of these two apparent position. Okay, it is actually the combined image of these two. Okay, so you can get a star here and here. So from that shift, okay, or its RA and dec, we can calculate that P here. So we got the P. From that P, using this equation, that is D is equal to, actual equation is like this. If you take that triangle, you know that it is the sun Earth distance called 1 astronomical unit. So I am taking tan P. I don't know whether you know what is tan P. Anyway, I am writing this. That is the opposite side. That is 1 AU divided by distance. So just rearrange it. D is equal to 1 AU divided by tan P. So don't worry, anybody who doesn't know the what is tan, what is sine, etc. Don't worry about this. Anyway, you won't be asked any mathematical problem which is beyond your level. There might be mathematical problems can be there, but there won't be any tan P or something like that which is beyond your topic, because I haven't taught you what is tan P. So this is for the students who learned this. Okay, so just a second. Okay, so D is equal to what we can do 1 divided by, so finally if you change put the value of 1 AU, something like the angle conversion and all, so you can get a equation like this. D is equal to 1 P. This means that here the angle is measured in a unit called a second. Okay, so the angle is usually measured, you know that if you take a protractor, it is actually 180 degree and a single division is actually 1 degree. So this 1 degree can be divided into 60 small pieces, and that one piece is called 1 minute. Again, we can divide it into 60 and one piece is called 1 second. So it is actually 3600 of a degree is called a second. So if you put that value in seconds, so D is equal to 1 divided by P, then you will get the answer in something called a parsec. So parsec is actually another kind of, like light year, this is another unit that is used by astronomers. So this is the definition for 1 parsec, is the distance from which the radius of Earth's orbit 1 AU subtend an angle of 1 second. So just leave that. The definition can be noted. Or if you want to define 1 parsec, I can do that. D is equal to 1 divided by, if I give P is equal to 1, then this is 1 by 1 parsec. So now, so when P is, okay, in this equation, when P is 1 second, that is called the parallax. d is equal to 1 parsec. Okay, so 1 parsec is actually 3.26 light years. Okay, so especially for the distance of other galaxies and all, usually astronomers use parsec instead of light years. Okay, so this is about it, and just leave that problem. Okay, now the problem of this, as already mentioned, this is the maximum we can have. Okay, so this is the maximum we can have, that is the maximum possible that diametrical distance. So, or 2 AU is the maximum we can have. But what if you want to measure the farther objects? Okay, we cannot employ this parallax method, because the measurement or the angle, the parallax angle or the P angle is so tiny, so that we cannot even detect it with the, our instruments. Okay, so we have to employ another method for finding the distance to far away objects. So that is why we have another method. They commonly called either, I am actually giving you a common method, and which can be classified into many types. Okay, so they are called standard candle methods, or simply flex luminosity method. Okay, we'll explain why it is called a standard candle and why it is called a flex luminosity. Anyway, we got two words that is called, one is called flex and other is called luminosity. Let's learn what they are first. Okay, flex and luminosity. So suppose there is a light bulb. Imagine that there is a light bulb, and I don't know whether you have heard that every light, even LED or what kind of light, so it is written as some 100 watt or something like that. Okay, so usually that is the energy consumed by it. Anyway, it is supposed to be, it should emit energy, 100 watt of energy. But for a usual bulb, the problem is that it emits not just the visible light, it emits other kind of light as well, that is infrared and all. That is why it is not that efficient. Anyway, assume that it is emitting 100 watt. That means it 100 watt means, what is the unit of power? Okay, so that is called, it's on the honor of the name, the person James Watt. So this is the watt, means joules per seconds. Okay, so you know that joule is the unit for energy measurement. So power means how much energy is emitted every second. That is, so when it is set 100 watt, means that it is emitting 100 joules of energy every second. So that is actually the light emitted by this bulb. So that actual energy emitted, or the real energy emitted by that light, is called luminosity. Okay, instead of light, because we are dealing with astronomy, we can change it to an astronomical object. Okay, so luminosity is the total amount of energy emitted by an astronomical object per second in all directions. Okay, it is not just in one direction, in all direction. Usually if you take a case of a star, it is spherical, so in all direction it is emitting energy, and the total amount of energy emitted by that astronomical object per second is called the luminosity. Okay, and its unit is watts. Okay, and for this case of sun, you can see that 3.86 into 10 raised to 26 watts. Okay, so that is the luminosity of sun. Okay, so you got it. So this is the luminosity of sun. So you just see that value, that is 3.846 into 10 to the power 26. That means 1 followed by 26 zeros. That huge the sun's luminosity is. But luminosity doesn't mean that we are receiving that whole energy here. Okay, just assume that if you are sitting on Earth, we are actually not receiving all the energy from the sun, because of many different reasons. One reason is that if sun is emitting in all direction, okay, we are sitting only at this direction, so we get only light coming in this direction. So already some part is gone. And the second thing is that if you go farther away from a light source, okay, any light source or any energy source, what we receive is less. Okay, if you, that means, in other words, we can say that Mercury, the planet Mercury, receives more light when compared with the Earth. Okay, that is why in Mercury we cannot have liquid water. At the same time, if you go to something like the Neptune or something, it doesn't, almost nothing, or it gets only a very tiny part of the sunlight, so that the water cannot be stay as liquid water. It will be cold, so cold there. It is ice there. Okay, so that is one reason. Okay, so the distance, as you go farther and farther away, we cannot get that entire luminosity here, and we receive only a part of the actual energy emitted. Or in other words, we can say that we receive only a part of the luminosity. So that part of the luminosity that we received here is called flux. Okay, but there is another problem. Okay, so part of the energy means, so imagine that this is again a light bulb. Okay, this light bulb is so simple to imagine, that is why I am taking light bulb. Okay, some spherical light bulb, and I am at a distance of 10 meter. Okay, I am here, my friend is here, we are both are standing at the same distance of 10 meter, and I am holding a paper of side 5 centimeter. Okay, a square paper of side 1 centimeter, and my friend is holding a paper of side some 8 centimeter. Okay, so in both the paper, in my paper and my friend's paper, in both of them actually the sunlight is falling. Okay, it's fine. And since the distance is same, so the energy is receiving is almost all the same, but who gets more light? Who is collecting more light? Obviously, we know that my friend is collecting more light because of the area. So if I have a larger collecting area for my telescope, I can collect more light if it is an astronomical object. So it depends on the size of the telescope that you use. So that is why we are actually making it, instead of using that, okay, instead of using since it depends on, or the light we receive here depends on the receiver. Okay, that again, here the receiver is this 5 centimeter paper, here it is the 8 centimeter paper. So the amount of energy that we receive here depends on the distance, obvious, because if you are farther away you get less amount of light or the energy, and if you are using a big area to collect light, you get more energy. So to make it independent of area, we have to find the energy passing through unit area. So flux is defined not just the light energy, amount of energy received here, but the amount of energy received per unit area per second. Okay, so that is, since it is there is a in a unit area, the unit is actually joule per every second per meter square, or joule per second can be called as watt, or watt per meter square is the unit. And you can see that 1361 watt per meter square is the solar flux. This is called a solar constant as well. This is also known as the solar constant. Okay, so this much amount of energy per second, or already per second, okay, is received. If you place a 1 meter square area something in the Earth's surface, then it will receive on average 1361 watts, and it depends on many factors as well. You know that when in summer you may get more, and in winter you won't get. It depends on your latitude, etc. That's okay, but anyway, on average this is the value of the flux that is received from the sun. Okay, so now you can see that. Okay, so now the flux is independent of the area. Okay, because we divided it with area to make per meter square, so there is no problem with the collecting area, but still it depends on the distance. So now we want to find how the flux and luminosity are connected through distance. Right? Okay, so for that, let's do some interesting derivation. Okay, so assume that this is the sun. Okay, and sun or any kind of thing. Okay, so its energy emitted is L. Okay, that is the luminosity, that is the total energy emitted per second. Now I want to calculate how much I receive here. Okay, so imagine that I am placing a 1 meter square. So what is the size of this 1 meter square area here? So energy falling on this 1 meter square paper or some telescope or whatever, that is, okay, once again, L is the amount of energy emitted by that star. Okay, and I am keeping a telescope here, and that telescope has a collecting area of 1 meter square. Anyway, this entire L won't come to my telescope, because there is a distance in between. Okay, so I can call it as the distance d. Okay, now this small 1 meter square area receives some amount of light. Okay, and that some amount of light is called the flux. Okay, so energy per second through that 1 meter square area, I can call it as the flux. Okay, now I want to calculate the flux. Okay, for calculating the flux, I am doing an interesting thing. So I am assuming not a circle, actually a sphere. Okay, just see, I'm assuming a sphere. Okay, I'm assuming a sphere. So what is the total energy? So I am assuming a sphere, and that sphere includes my small 1 meter square as well. Okay, and it is a so big sphere with the distance as the diameter. So it is something like this. So I will draw a vector picture. So you can imagine this is the star. Okay, and let's imagine a big circle like this. Okay, let the sun be at the center, and here we have that small area here. Okay, 1 meter square, and this distance is d. Okay, now this is not a circle, you have to imagine it as a sphere. Okay, now what is the energy emitted per second? It is L. Okay, so this L energy is actually spreading outward like this. Okay, and when it reaches at a distance of d, actually that entire L is actually giving, or it is spreading all over that sphere of radius d. Okay, that means suppose you have to assume that there is no other things in between, and just take this case. So when it reaches here, okay, so light is traveling in this direction, in all direction it travel the d distance. Okay, and when it reaches at the d distance, okay, or at that distance, that entire light is actually spreading over that big sphere of radius d. That is an imaginary sphere again, okay, because we assumed it. So what was the total energy emitted? L. That is divided or spread all over the surface of the sphere. Surface of large sphere. Okay, large sphere. So what is the surface area of that sphere? Surface area of sphere is actually 4 pi r square. Here r is d, so that is 4 pi d square. So this is the energy that is falling over that surface, and if you consider if it is on what is, this is per area, and per meter square, again I have to multiply it with 1, so that I get L by 4 pi d square. This is the flux. So flux is equal to that total L spread over this 4 pi d square. Here d is the distance to that object. So now we have connected flux with the luminosity through d. See, this is it. So now you can imagine it like this. See, this is the okay, as you go farther and farther, you can see an interesting thing. The same energy is actually spreading for a larger and larger sphere. That is why the light is getting dimmer and dimmer when you go farther and farther away from the object. So we got a relation, F is equal to 4 pi r or d, whatever it is. This is the distance. R is the distance or d is the distance. Now F is equal to L divided by 4 pi d square. The d is better to avoid the confusion. For d we can use the distance. So rearrange this so that d square is equal to 4 pi f, or d is equal to square root of L divided by 4 pi f. So what is d? D is the distance. So if you know the luminosity, the actual energy emitted by an object, and the flux is so simple. You have to put a telescope here and measure the energy passing through that per second and per unit area. That is easy. And if you know the flux and if you know the luminosity, then just take the ratio, multiply it with the divide it with the 4 pi and find the root and all. Then you can actually calculate the D. So simple equation. Okay, so this is the method. So if you know the luminosity and flux of an object properly or simultaneously, then we can actually measure the distance to that object. Okay, but here the equation is so simple. Maybe at the with a high school level mathematics we can derive the equation and all. Maybe it is understandable, but there is a big catch here, or a big problem is here. That is how we know the actual energy that is coming from a star or a distant object or a galaxy or whatever object we are observing. We need to know the real energy coming out of it. Okay, so that is why we need some standard objects, okay, for which we know the actual luminosity or the actual energy coming out of it without knowing the distance. So if you know the distance, okay, you know that this is an equation. In this there are three variables, that is d, l and f. If you know the flux and distance, then you can easily calculate the l, no problem at all. But here the problem is that you don't know the d, you don't know the l, only you know f, that is measurable. So by knowing f only, you cannot find either d or l. You cannot find both. At least you have to know two of them to get the other. So for distance, you have to know L and F. So the problem is that we don't know the L. Okay, so we cannot go and measure the actual luminosity of objects. So that is where we need some kind of objects that are used, that are basically without knowing the distance, we know the luminosity. So already luminosity non-objects are there. They are called standard candles. Okay, the name is standard candles. Okay, because its value is already known, that is why it is called a standard. Okay, or its luminosity is already known, which is called standard candles. Okay, now the problem is which object that we can use. So one method is that I will roughly say it here, this main sequence fitting. I will explain you it later when we learn about I will give you a glimpse of HR diagram. So this is a kind of a diagram called the HR diagram. Okay, we will discuss it in the syllabus of that stars and all, so don't worry. So it is, you can see that it is the surface temperature and the brightness. So from this surface temperature, we can actually find out, if you put a star into this graph, and we can find the energy emitted. That is one method, that is called the main sequence method. It is not that simple. You have to find a star cluster and all. It's a bit complicated, not that easy. Anyway, this is one method. But much more efficient and better method is there, that are using one kind of a star called a variable star. Okay, they are called as Cepheid variables. So what are Cepheid variables? These are stars pulsate with a regular period, and their luminosity is directly related to their period. Okay, so here you can see what are they? They are actually stars. They pulsate with their regular period. You can see the graph of that here. These are the observation date: 621, 625, 629. So this is almost, you can see, or the 625. Then another peak in 75. So from this you can see that its period is, or its brightness is varying like this, up and down and up and down. And from that up and down, you can see that the time taken for the two peaks, that is called the time between the two peaks, is called the period. So for this star, it is actually 9 days, almost 9 days. Okay, so 9 days is the period of that star. So there are stars which pulsate with a regular period. Okay, there are stars which pulsates, but it should be with a regular period. And there are different types of Cepheid variables are there. Anyway, Cepheid variable stars are the stars which pulsate with a regular period, and their luminosity. Okay, see, its luminosity is directly related to its period. Especially if you look at here in this gap, I'm not going to explain this. This is almost a straight line. Okay, that means here, if it is 50 days, its magnitude is -4. Absolute magnitude means it is something like a luminosity. I haven't mentioned what is the magnitude scale here. Anyway, you can imagine it as the luminosity. So I got the luminosity. So I can measure the 70. Suppose 70 is the period of a star. Then I can use this graph, then draw a line. I got this. And if one star has some 90, then it meets here. I can find it. So this is how I can find the luminosity of a. So, and you can see here two lines. One is for the classical Cepheid, and there is another type 2 Cepheids are there. There are two types of Cepheids, but scientists are able to identify, even though it is pulsating, which type of Cepheid it is. So by this graph or something, they can easily find out what is the actual luminosity of those stars. Okay, so from those luminosity, so now we got the luminosity. Now we have to measure the what is called now we have to measure the flux from here. Use a telescope and measure the energy falling on that, and which is called the photometry. That method is called photometry, and using that you get the flux. So flux you got, luminosity you got, then you can calculate the distance. So that is how the distance are calculated using standard variables. But even though the equations or the idea concept is so simple, it is not that easy. There are some many other things are involved in this, even though it is not that accurate even. But for this kind of large distance, maybe some 10% error is okay, or it is acceptable for us in that case. So that is how the standard Ceph candle method, that is Cepheid variables, are working. But beyond Cepheid variables, there are some other thing that is called type 1a supernova. So this is a kind of a supernova. Supernova can be classified into different types, and one of the type is type 1a, which happens when a white dwarf star accretes material from a nearby giant star, red giant usually, and it gets more and more matter and get massive, and finally it collapses into a supernova. So that what is called that explosion has a speciality. If you check the brightness of that, when the supernova is at its peak, its brightness is fixed. Okay, that means for all type 1a supernova, its peak brightness is the same. Peak brightness is the same means the peak luminosity, we can find it out. Okay, so the for type 1a supernova, the luminosities are same, more or less same. Some small difference are there, but it's not a problem for the distance measurement. But from that peak luminosity, we can find out the what is the actual luminosity. So from peak brightness, we can get the luminosity, and from that luminosity, we can get the flux. We can measure the flux here. Already we got the luminosity from its peak. So peak luminosity is there, flux is there, so the distance is there. So that is the next method of type 1a supernova as standard candles. So these are all the methods that we employed in what is called the, where is the distance ladder? Yes. This is the white dwarf supernova methods. Okay. And the next one is Hubble's law method, and that we will discuss, will be discussed in the cosmology class, because we need to learn the Hubble's law. Okay, so that's about it.